Good evening, class. This is Adam Ward, and I want to talk through example 2 from our lecture about forces on inclined planar surfaces. And so the image that you had in your course pack is shown here on the screen on the left-hand side. We're given a concrete block holding back a layer of water, depth h. The concrete block is width b, and the question we're asked is to find a relationship relating the width b that's required to prevent the dam from overturning. And so when we did our motivation for this lecture, we talked about the Hoover Dam and wanting it to both not slide and not tip. That's why we wanted to learn about the line of action. So in the bottom left, you can see I've started a free body diagram. I started with forces in the x dimension, the resultant force pushing from the water onto the concrete, and a friction force that would be resisting that. So the concrete sliding across the ground surface. If we continue in the y dimension, there are two equal and opposite forces acting. There's the weight of the concrete dam that's acting down through the centroid labeled F sub W, and there's a normal force. This is essentially the ground pushing back on the concrete. That's what keeps things static. Now, because we know that this is at a static equilibrium, we know the sum of the forces in both directions has to equal 0, and also because it's not rotating, the sum of the moments about any point also has to equal 0. Now, what we can do for this problem specifically is to analyze the system at the time exactly when it would be about to tip. And so you can envision that if you start pushing on a concrete block, the point that it would tip around, behaving more or less as a hinge, is what I've labeled as point A on the free body diagram. Also at that time, the normal force would be 0 because you'd be just beginning to rotate the block up off of the ground, and the friction force would be 0 because it's both acting through A and has no moment arm, and because you're rotating about point A, not sliding, so there is no friction force. So let's start on the right-hand side of the page with our sum of the moments equal to 0. Very similar to examples that we've done in class. We've got the resultant force, and that is pushing with a moment arm of h, the total height, minus y sub r. I've shown that in purple on the slide. And acting in the opposite direction, we have the normal force, the force of weight of the concrete. It's acting through the centroid, and the moment arm from A is the width over 2, B over 2. So in this equation, we've got three key unknowns that we need to be able to describe in order to solve the problem. The first is that resultant force, gamma HCA. That's fairly standard for us at this point. And what I'm including here is the depth to the centroid as h over 2. And we don't know the area because we don't know the width of this concrete block in and out of the page. And so we'll analyze a unit width, meaning 1 meter in and out of the page. So I've put an h times 1 meter for the cross-sectional area. The second key unknown for us is where that actually acts, the dimension yr. We've done this in example 1 in this lecture as well, using the equation you see with a 2 next to it on the screen. And we can look up the properties of a rectangle in the textbook, figure 2.13. And for our specific case, the width is the width that the fluid is pushing on. That's 1 meter in and out of the page. The depth is h cubed. And so that second moment of inertia, that moment of inertia can be termed h cubed over 12. We also need to know y to the centroid. That's the distance measured along the plane to the centroid, and that turns out to be h over 2. Now, making those substitutions back into our equation, we see that the resultant force acts 2/3 of the way down. This is actually a generalizable result for us. On a special case where we've got a vertical surface. If you look down at the free body diagram, I filled some dimensions in. For a case where we have a pressure prism that originates at the surface on a vertical wall, that resultant force will always act 2/3 of the way down and 1/3 of the way up. So you can use that as a shortcut as opposed to having to go through the steps that I've shown in orange and green on your current slide. The final item we need to deal with is the weight force pushing down on the block. And that weight is equal to the specific weight of the concrete multiplied by its volume. And of course the volume is h by b, the two dimensions that are shown, and again 1 meter in and out of the page. So when we take those three equations, we can combine them. So plug those three results into our first sum of the moments equation. We get what's shown here. And with a little bit of algebra, you can come up with the equation that I've boxed in red at the bottom center of the screen. This is a relationship for width as a function of the height of water you hope to hold back, and also a function of the fluid properties and the concrete properties. If you use the typical values that are given to you of 62.4 pounds per cubic foot for water and concrete at 150 pounds per cubic foot, you come up with a generalizable relationship that suggests the width, B, needs to be about 37% of the height to prevent overturning, and in a typical design problem you'd put a factor of safety on that to make sure that you were not just at the tipping point but well before that tipping point in your design. Again, with the Hoover Dam in mind as our motivation in this lecture, you can imagine why the width at the bottom needs to be more than 600 feet, even though the top is only the width of approximately a 2-lane roadway. Thank you for your time and attention, and as always, I hope this helps you.